In this video, we are going to discuss problem based on Atwood machine. An Atwood machine is a device that have masses attached to a rope that passes over a pulley as shown in the figure. The question says a 5 kilogram and 10 kilogram mass are attached by a string that is stretched around a pulley. Determine the acceleration of the objects and the tension in the string. So here you have masses M1, which is 10 kilogram, and M2, which is 5 kilogram, attached by a string that passes over a pulley. And we need to find what is the acceleration of these masses as well as the tension in the string. Now, since these masses are attached by the same string, the tension force exerted on them by the string will be equal. So I can show the direction of tension forces towards the suspension point, and the magnitude of these tension force will be T. It is the same for both masses as they are both tied by the same string. We need to find acceleration of these masses, so I'm going to first assume the direction of acceleration. Since M1 is heavier than M2, I'm going to assume that M1 is accelerated downward and is pulling M2 up, so its acceleration will be upward. Both masses have the same value of acceleration because they are being tied by the same rope. So the rate at which M1 comes down is the same rate at which M2 will go up. Now this is the direction of acceleration that we have assumed according to the figure. If the actual direction of acceleration is opposite to what we assumed, the answer that you will get will be negative, but the magnitude of acceleration will remain the same. So before we solve the problem, I will first draw the free body diagram for the forces acting on both M1 and M2. So let us start with M1. The first force that we show acting on any object is the force due to gravity. So I have the force due to gravity acting on M1, which is directed vertically down. I write this as Fg1. The second force is the tension force exerted by the rope, which is towards the suspension point. So it is acting in a vertically upward direction. I call this force T. We do the same thing for M2. Again, the first force acting on M2 will be force due to gravity acting vertically down. We write this Fg2. And the second force will be the force of tension directed towards the suspension point, which is again written as T. After we draw the free body diagram, we will write the equation of net force for both the masses. When an object is accelerating, the equation of net force for that object can be written as F net equals m into A. So we are going to write this equation for both mass m1 and m2. Let's start with m1. Since it is accelerating, we write F net 1 equals negative m1 into A. The negative sign here because acceleration is a vector quantity, and since it is a vector, we have to take its direction into consideration. Here, acceleration for m1 is pointing down, and we know by convention, upward direction is taken positive and downward is taken as negative. So I have to take this acceleration for m1 as negative. Then we find the net force. Forces acting on M1 is the force due to gravity Fg and the tension in the string. So to write the net force acting on M1, I have to take the vector sum of these two forces. Now when I say vector sum, I will add these forces, but I need to take their direction into consideration. And again, by convention, all forces pointing up, we will take them as positive, and the ones pointing down will be taken as negative. So I can write F net 1 as sum of the tension force and force due to gravity. Tension, since it is pointing up, I take it positive. Force due to gravity Fg, since it is pointing down, we take it negative. Fg1 equals minus m1 into A. Fg we know is given as m into g. So I will substitute that here. T minus m1g, m1 because this we are finding for mass 1. equals minus m1a. Move m1g to the other side, we get T equals minus will become plus m1g minus m1a. I will call this as equation 1. Now we do the same thing for mass 2. I will write F net for 2 to be equal to m2 into a. Again, we are writing this as m2a because the object is accelerating, and here the acceleration is positive because for m2, a is pointing in the upward direction. Now for F net, again we take the vector sum of two forces acting on m2, which is the tension force and force due to gravity. Since tension is pointing up, we take it positive. Fg is pointing down, we take it negative, equals m2a. Substitute for Fg as m2 into g equals m2a. Move m2g to the other side, you get T equals m2g plus m2a. I will call this equation 2. So if you look at equation 1 and 2, in both equation we have T equals something on the right hand side and T equals again something on the right hand side. So if the left hand side of both equations are equal, the right hand side will also be equal. So we can say that equation 1 is equal to equation 2, and we can equate the right hand side to solve further. I will write m1g minus m1a to be equal to m2g plus m2a. Then move all the terms with a together and all the terms with g together. So I will move m1a here and m2g on this side. So we rewrite this expression m1g. When you move m2g to the other side, it becomes negative m2g. And when you move negative m1a to the other side, it becomes positive m1a plus m2a. We need to find the acceleration, so we can take the acceleration common from both the terms here, as well as you can take g common here. So we get g m1 minus m2 equals a m1 plus m2. Now divide by m1 plus m2 to find a. You get a equals g m1 minus m2 over m1 plus m2. So this expression here for acceleration is the acceleration for masses in an Atwood machine. You can directly use this expression to find the acceleration, or you can arrive at this equation by solving the way we did right now. So now let's substitute. A will be equal to G is 9.81, M1 is 10 kilogram, M2 is 5 over M1 plus M2, which is 10 plus 5. And when you solve this, you get the acceleration A to be equal to 3.27 meter per second squared. And since this acceleration came out to be positive, that means the direction that we assumed in the beginning was correct. If it wasn't correct, this acceleration would have been negative. So this completes part A of the question, where we wanted to find acceleration. Then in part B, we need to find what is the tension in the string. Now we have two equations for tension, equation 1 and 2. And since I already found the acceleration, I can substitute this value of acceleration in any one of the equation to find what is t. So let's substitute the value of A in equation 1 to find t. We write tension T equals m1g minus m1a. Let's take m1 common, g minus a. Now substitute m1 is 10, g is 9.81, and a is 3.27. After you solve this, you get the tension in the string to be equal to 65.4 Newton. And since this tension is same on both sides of the string, we just have to calculate it once. So this is how you find the acceleration of masses and tension in the string in an Atwood machine. You can divide this problem into steps so that it becomes easier to remember. Step 1 will be to draw the free body diagram and show the direction of acceleration as well as all the forces. Step 2 will be to write equation of force for both masses. Then step 3 will be to equate those equations. If you rewrite equation of forces in terms of tension, you can equate them together to solve for acceleration. Step 4 will be to solve for tension by substituting the value of acceleration in any one of the equation for tension.